So, we're going to start today by talking about the states of matter. Now, I know this is something that you probably have covered since you were a little kid, where we're going to talk about solid, liquid, and gas particles. And a lot of times when you're a little kid, and even throughout your years in school, we talk about it and we think about ice, right? Ice is a solid. When it melts into liquid water. And then if we boil it or we leave it out to evaporate, it becomes a gas. So, you can keep that in mind as we go through these. But the most important part to keep in mind is the kinetic molecular theory of matter. The word kinetic means movement. So, this is the movement of molecules. It is the idea that all particles of matter are always in constant motion. So, you can imagine these particles are kind of just buzzing around at different speeds, maybe in different directions, and they're all traveling around. They will continue in the same direction that they're going until they hit something, in which case they will bounce off and go another direction, kind of like a pool ball. Matter can exist on Earth in, I say, three plus phases, right? We've got gases. Gases take the shape and volume of their container. So if you were to have a water bottle, and in your water bottle, that's a terrible picture of a water bottle, you were to have gas particles, it would fill up the entire water bottle. If you were to have that same water bottle and put instead liquid in your water bottle, that liquid would not take the volume of the container, but it would take the shape of the container. And lastly, a solid takes neither the volume nor the shape of the container. It stays in its own volume and its own shape that it came in with. The kinetic molecular theory of matter applies to all three. That means that gas particles move, liquid particles move, and solid particles move. So here's again kind of a representation of the three states of matter and what they look like. Solid particles are usually, we say, they're tightly packed together, they're kind of close together, they're organized and neat. Liquid particles are still pretty tightly packed together, but they're not as organized and they can slide past each other easily. And gas particles are more spread apart and they're going to fill up the container. So you can think about that container again, not the shape nor the volume. This one takes the shape but not the volume. This one takes the shape and the volume of its container. So let's talk about what it takes to move from these different phases. You've got gas, again, liquid, and solid. So I want to point out some words that may be familiar to you. When you have solid like an ice cube and it turns into liquid, we call that melting, right? And when you have liquid and it turns into a solid, we call that freezing. So those are familiar words to you. When you have a liquid and it turns into a gas, we're going to use this general term vaporization, okay? Now you might think evaporation or boiling, and we'll get into that later, but let's just use the general term vaporization. And if you go in the opposite direction, if you turn a gas into a liquid, that's called condensation. And this is probably one of the trickier ones that people can't picture as easily. Condensation happens, the best example of condensation is when you have an ice cold glass of water and you've got it on a hot summer day, and along the outside of that ice cold glass of water you're going to see little water droplets forming, okay? What's happening there is that the gas in the air is condensing on the side of the glass. So that's a good example of condensation. Now, another two words that we have here that might not be as familiar, we've got sublimation. Sublimation is when a solid goes to a gas, and when a gas goes back to a solid, we call that deposition. Now, pay attention to these colors here because these are important. The green ones represent an exothermic change. Exothermic means that heat is released. And And the blue arrows represent an endothermic change, which means that heat is absorbed, right? So if we look at these, if we melt and we go from a solid like an ice cube to liquid water and we are melting, that is an endothermic change. That means that heat is absorbed as we're melting. A liquid back to a solid means that heat is released. This one is really tricky for people because they think of freezing as cold, and when things freeze, they get cold. But really, when things get frozen, when they move from that liquid to that solid, it means that they're going to actually release some heat. Condensation is exothermic, heat is released. Vaporization, which includes evaporation and boiling, means that heat is absorbed. And we have heat absorbed through sublimation and heat released through deposition. So the word temperature is a little bit tricky in science. It is defined as the average kinetic energy of the particles, right? So if you were to just have, a block of something, let's stick with ice again. Within that block of ice, you would have the water particles that made up that block of ice. Now, those water particles, according to the kinetic molecular theory, which, by the way, is abbreviated the KMT, those water particles are moving, they're jiggling, they're kind of sitting in place, vibrating. So, temperature is that measurement of the vibration. It's the kinetic energy or the movement of those particles. And we do have three scales in science class: Fahrenheit, which is degrees Fahrenheit. Celsius is the one that you've always kind of learned that you use in science class, and that's degrees Celsius. And then the Kelvin scale, which is absolute temperature. It does not include degrees. That's just Kelvin. These two scales are what we are going to use in this class the most. This one we pretty much never use in science class, but I know you'll use it in your everyday life. If we were to take something like room temperature would be about 72 degrees Celsius. Room temperature would be about Fahrenheit and 25 degrees Celsius. So those are very different from each other. Kelvin and Celsius have the same distance between the degrees. Room temperature is 298 Kelvin, which I'll get to in a second how you convert that. The Celsius scale is based on water's freezing and boiling points, right? So we know that water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius. So everything there in between is going to be either really cold water or hot water, right? So beyond this, water turns into a gas when it is at the proper pressure, which we'll talk about. And below this, water turns into a solid. And this area right here is liquid water. Kelvin gives a more direct measure of the average kinetic energy because there is no negative. Okay, there are no negative numbers in the Kelvin scale. We call it the absolute scale because we know that 0 Kelvin is what we call absolute zero, and that's zero that doesn't say okay. And there are no negative numbers. So absolute zero has been estimated at approximately negative 273 degrees Celsius, and that is the coldest temperature. It's where all motion stops, right? So we get no kinetic molecular theory happening here. There's no movement of the particles. So this is an important thing to remember when we convert from Celsius to Kelvin, which you're going to be doing a ton in this class. You just add 273 to the Celsius number. So if you'll remember, I said that room temperature is about 25 degrees Celsius plus 273 is going to give you about 298 Kelvin for that room temperature amount. And you can go back in the other direction. You can take the Kelvin scale and subtract the Celsius. So, if we're talking about temperature and the kinetic molecular theory, remember I said that these particles move faster when the temperature goes up. So you can picture here these particles that are kind of bouncing around in all these different directions. If I were to raise the temperature, these particles would start moving faster and faster. If I were to lower the temperature, they would slow down. Again, if I were to go all the way to absolute zero, those particles would stop. Now, there's something else that affects these particles. These particles are also affected by pressure. And pressure is, something that we talk about. You might think about pressure under the ocean or the pressure as you go up in an airplane, but pressure mathematically is defined as force divided by area. So if you were to think about three pairs of shoes and you were to ask yourself, which shoes create the most pressure? If I was going to step on someone's foot, what would I not want to step on someone's foot with? Hopefully you thought about these ones, right? To step on someone's foot with a little tiny area of the back of that stiletto heel would hurt so bad. That would really, really, really hurt. So this one is going to create the most pressure. These over here, in case you didn't even know what these were, these are supposed to be snowshoes. And people wear snowshoes so that they don't sink into the snow. So they do the opposite. They increase the area and it makes it so you can walk on snow. Good luck walking on snow in your heels. So the snowshoes would have the least amount of pressure. And that's because the snowshoes have the greatest area, while these have the least area. So you can see there the way this is related in that formula. A barometer is a measurement tool that we use to measure atmospheric pressure. There is a mercury barometer, which would be very old school. You've got the pressure from the atmosphere pushing down, and there's mercury going up here in this column, and it tells you what the pressure of the atmosphere is, the atmospheric pressure. This one is a little bit more complicated, but I have one in class that we're going to look at a little bit later and see how this works to measure the atmospheric pressure. Now, speaking of atmospheric pressure, I mentioned airplanes, right? If you are in an airplane, again, kind of a terrible picture of an airplane, and you are down below. Um, as you go up in the air, okay, there will be less air particles above you and more air particles below you as the airplane were to go up in the air. So the pressure of the atmosphere goes down as you go up in the air because you don't have as many atmospheric particles sitting on top of you. Here on planet Earth, you are used to living at a certain amount of pressure. So you are used to having this atmosphere kind of sitting up on top of you. Um, if you don't have that atmosphere sitting up on top of you, your ears pop, and then I suppose other horrible things could happen because your body would be not used to that pressure. So pressure becomes really important to think about as we move forward. At sea level, we always have to have a standard that we talk about in science class and in chemistry class. Sea level would be not too high in the plane, not too low in the plane, not under the water. It would be like just right. This is considered standard pressure. So remember, we talked about standard temperature and pressure. Well, sea level is where standard pressure happens. And standard pressure is 101.325 kilopascals. I really prefer this one atm. That's a little bit easier to remember. 760 millimeters of mercury, 760 torr. These are actually the same value. Or 14.7 psi, which stands for pounds per square inch. So this is not a very sciencey one that we talk about very often. Honestly, in this class, we're going to be using the first three. But what I've given you here is I've given you conversion factors. So if you have to convert 2 ATMs, to millimeters of mercury, you're going to go ahead and use a conversion factor that we've been using all year. So you say, okay, fine, for every 1 atm, there are 760 millimeters of mercury. And in order to solve that, there's your ATMs cancel, so you just get 2 times 760. A Pascal, in case you're wondering, a Pascal is a Newton. This is a unit of force, is a Newton, over a meter squared, which is a unit of area. And remember, we talked about pressure being force divided by area. A kilopascal is just 100 times the Pascal. So let's take a look here at this phase diagram for water. These are a little bit tricky. I think the very first time you look at them, they can be really overwhelming. We're really used to thinking of water as just solid, liquid, and then gas, okay? And where that happens, where solid, liquid, and gas happens, is right here. This is that standard pressure, okay? So there's 101 kilopascals. And you can see here that water is a solid until it hits right here, which is, it's hard to see, but that's 0 degrees. And then it becomes liquid water until it reaches right here, which is 100 degrees Celsius. And then finally, it can be a gas all the way from 100 degrees Celsius and beyond. But now that you're a little bit older, I need to tell you the secret of water. This is only at standard pressure, which is what we're used to living at. If you were to bring yourself to a much, much, much higher pressure, the temperature at which ice turns to water would happen, you can see here, at a lower temperature. So, like maybe, I don't know, -10 degrees Celsius or something like that. And if you were to lower the pressure way down, you're actually going to reach something called a triple point. And the triple point is where the water is existing as a solid, liquid, and gas all at the same time. And you can see here, here's where sublimation happens with water, which is not something we usually talk about. It's when a solid turns to a gas. So that's where sublimation comes from. So to put it into more familiar terms, here's a solid turning to a liquid. We call that melting. A liquid back to a solid is freezing, right? A liquid to a gas is vaporization. A gas to a liquid is condensation. And here's where sublimation and deposition happen. Again, the triple point is a very special point. It's the point at which all 3 states of matter exist. The critical point is when the temperature and the pressure are both so high that the particles actually start to break down. So here is a phase diagram for carbon dioxide. All right, so carbon dioxide, which is CO2, is what we call dry ice. All right, and when you go to the grocery store, I think you have to be 18 to buy it. This is dry ice, okay? And this is now, we've switched. The pressures are now in atmospheres. The pressure is not measured in kilopascals. So here is standard pressure, or pressure at sea level. So dry ice is a solid until it reaches about -78 degrees Celsius. So dry ice is very, 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 very cold at standard pressure, which is what we pretty much exist at. That's why dry ice will sublime, right? Dry ice does not melt. Dry ice turns from solid carbon dioxide into gaseous carbon dioxide. In order to get dry ice to melt, we would have to raise the pressure all the way to 7 atmospheres, which is pretty high. So, not that it doesn't exist, you just have to change the pressure of things. So, back when you learned solids, liquids, and gases, you thought of it as a linear thing, that it always went from a solid, a liquid, to a gas. And now we've got to think about this sublimation that happens at different pressures.